Are you a food science major?
Yes, sir. Yes, ma'am.
That's fun.
How
That
did you
sounds great.
how did you know that?
Well, because I saw food science and food science.
Oh yeah, yeah. I'm food science major. Okay, okay. So, let's see.
I feel like that's an underrepresented major.
Yeah, apparently it's pretty small, I guess. But UMass has a really good food science program, apparently.
Oh,
I don't know. This is like my first real semester being a major, so. Okay,
all right.
so, question number two, which is really question number one.
Yeah.
So, two identical currents travel in the directions shown, up and to the left. What is the direction of the net magnetic field at the point labeled with an X? So, it is out of the screen.
Yeah.
Okay, yeah, just because it's perpendicular.
Yeah, that's what I said.
Yeah. I just used like the right hand rule.
Hmm.
Yeah, didn't you put your hand in like the direction of the current and you push where your palm is going?
Oh,
I
that makes sense.
no, I did the other one, the other right hand rule. So if I put my thumb in the direction of the current, then the way my fingers curl is the way the field goes.
Okay.
So
Yeah, there's like two ways to do the right hand rule.
yeah, so for the vertical one, it's coming out of the screen at the X.
Hmm.
Mhm.
And for the horizontal one, it's also coming out of the screen at the X.
Yeah.
All right. Um. Oh, okay. All right. I got this one right as well, but I'm not. I kind of just took a guess.
Yeah, I didn't do very well on this one, I think.
Okay.
Let me check to see if I got that right.
So,
I'm gonna be real, this chapter kind of ate my ass.
Oh,
This is gonna
so
be a fun recording to watch, but it
well,
was like
I've
really
missed everything too. I've
oh,
been like such a bad student. I've been like attending all of the classes up until this chapter. And
oh
it's
man.
really. I attended all of the first chapter, none of the second chapter, and like most of this section.
I go to class. I just don't pay attention all the time.
Okay, I feel that
So,
too.
it's
When
tough,
I go to
man.
class, I just kind of sit on my phone and wait for the
yeah.
90.
Like it's 10 a.m. too. All right. So
Did any of us get this?
I got it right. Let's see. Where's my equation sheet? Okay. So what you do is you take the first V,
Mm-hmm.
which is 25.7, then you subtract V2,
Oh, okay.
and then that is what. Okay, okay. No, then there's an equation that for capacitance, which is C equals Q over delta V.
Mm-hmm.
And so the delta V is the 25.7 minus 2.5, and we're trying to find the Q.
Right.
So,
Well, I was just confused because the terminals are facing the same way. Like it's in parallel, not series. So I didn't know to like add it or subtract it or what.
I was confused by that too.
okay, I think I get this now. So it's C equals Q over delta V, which means it's the change in the voltages,
Yeah.
Yeah.
which, and since the two voltages, or the batteries, I guess, they're going in opposite directions, you subtract one from the other,
Oh, okay.
and it doesn't really matter which one you subtract from which, because if you do the wrong one, quote wrong one,
Yeah, it's
then
negative,
it'll just
right?
be negative. Okay.
Yeah.
So that's 2 point,
Right.
wait, 25, 25.7 minus 2.5 is 23.2, and then you multiply that by 2.5, you get 58.
Yeah,
Yo, Warframe
because
is
you
saying
want to isolate the Q, so it's C is equal to Q over delta V, so you just multiply it by the delta V.
Yeah. All right.
Okay, that makes sense now.
yeah.
I did not get this. Number 4.
Yeah, I got the wrong number, which like blew my mind because I had never gotten one of these questions wrong in my life, but just that one. I did 1 over I plus 1 over O equals 1 over F, but I'm assuming I just mixed up like the object distance and the image distance.
Yeah, I did too. So I did the I put I as 90 and O as 25.
That's
So
what I
you
did
have
too.
to do is you have to solve for the focal length first.
Right.
You have to do 1 over 25 minus 1 over 97.2.
97.2.
And then 1 over that answer will
Oh, the numbers are different.
Oh,
focal
okay.
length, right?
Per practice.
And then you put that back into the object. 1 over I plus 1 over O or whatever.
Wait, sorry, could you say that again? It's 1 over 25 minus 1 over...
Yeah.
Why are you subtracting it?
That was solving for the focal length.
Okay,
The focal length, you would still add it, wouldn't you? Because it's on like the other side of the equal sign.
So what is the 25 centimeters and what is the 90 centimeters?
So I was assuming, I think there's an equation for like focal length.
Let's see.
You can just solve for focal length using the 1 over I plus 1 over O equals 1 over F thing.
Yeah. All right, this is for mirrors. Yeah, I did the 1 over I plus 1 over O equals 1 over F.
Oh, I know what I did.
Mhm.
So you can solve for I use the equation. I found this because you were allowed to use like anything we want to,
Mhm.
as long as we're not like actively putting our answers on Chegg.
Yeah.
I found this YouTube video, like a snapshot of this YouTube video. And what we could do is we have to assume that the 90, I believe, or no. We assume that the 25 centimeters is positive, but we have to assume that the 90 centimeters is negative. Works, we have to assume that's negative, and so that's how you get that. So it'd be 25 minus 1 over 25 minus 1 over 90 is equal to 1 over the focal length. And
Oh.
that, what?
Okay, so what does it mean when it's negative?
Yeah, I just got that. Yeah. The image distance is negative when it's like on the side of the incoming rays. So like with a diverging lens, it makes a virtual image like on the side. Like I don't know. It's hard to explain. Like I know exactly why it's negative now, but
Yeah.
you want to make an image seem closer than it appears. So technically, like closer than where the lens is. You know what I mean?
For this one, it's... Wait, did you have a question about nearsighted people? Because this one's about farsighted people.
No. This
Okay.
is the same.
And they're
Yeah.
all far-sighted people, I think.
Okay, so it's not... Alright, so the glasses are the lens,
Yeah.
and the light is coming from the side away from your face.
Yeah.
And then the 90 is on the side where the light came from. So that's why it's negative?
I'm like confusing myself here. I feel like I just had it like completely. So if you like drew a ray diagram of this, the object distance, the closest object distance would be 90, and then the image distance would be 25 from the eye. And why did I just confuse myself with this?
So
I could just go back in my notes.
I get why it's... Okay, no.
I don't know if it would be on the same side or the other side of the lens because we don't know how far it is.
Yeah. I don't know. I got it right, and I just assumed it was negative.
Okay.
Okay. I guess that makes sense. Yeah. So if the light is coming in to you, and the image is supposed to be 90 centimeters away, then it's negative because it's on the same side that the light is coming from.
Yeah, well, that's how you. Yeah, that's just like a negative image distance.
But
And it would be
that-
like a virtual image.
But then why is the 25 centimeters not negative?
Because that's like the first object distance, and that's where you want your.
Image to be.
Oh, that's true. Wait, this near point's 90 centimeters. Oh, you know what it might be is where we've been fucking up the terminology, right? Like, I think the 90, since it's their near point, that's where you would want your virtual image to be. Not like the 25 centimeters is not the virtual image. It's the 1/90 is the virtual image. So the 25 centimeters would be the object distance.
Yeah.
Yeah. So that, yeah, I think that makes more sense.
It's like I get that the minus 90 works, but I don't get why it is minus 90.
Because the virtual image is like further out from the lens. So if you had like a converging lens, the image would be inside of your eye, that it like where the light actually converges. But then with this diverging lens, it makes a virtual image further from the lens than what your object distance is.
Virtual.
That sounds like
Yeah, like so a converging lens, the light converges on the other side, like inside of your eyeball.
Okay.
But with this diverging lens, the light virtually converges like in front of your face.
Okay. So also, why is it a converging lens versus a diverging lens? I don't really get how to figure out which one is which.
A diverging lens, typically,
What
I
do-
just remembered that that's what they use for farsighted people.
I think the diverging lens is better for nearsightedness because it kind of, and the converging lens is
Oh, wait.
for farsightedness. So it's like because you,
Yeah, it's a converging lens with the focal point. So I've been
yeah.
lying this whole time too.
I know. I just kind of thought that one through. I just kind of was like, well, it makes sense if it wants it to converge sooner.
Yeah, I don't know. I've been hella wrong, man.
All right, so you got a converging lens here. But
Is
isn't-
nearsightedness where you want to make a virtual image then?
I don't know, because isn't the 90 centimeters, the object, supposed to be further away than the 25 centimeters?
Oh, yeah. So you can have I'm looking at it in my notes now. You can have a converging lens that also makes a virtual image.
yeah.
Okay.
You look up, if you just go on Google, I checked myself too. If you look up what type of lens do they use to treat farsightedness, it comes up with converging lenses.
So, okay, I'll remember that. Then a diverging lens is probably nearsightedness, right?
Okay. I guess that makes sense. All right.
Thank you, Google.
Yeah, thanks, Google. All right. Are we ready to go on to the next one?
Jesus Christ. I just made that so much worse for everybody. I was I realized that.
I mean, you just kind of need to plug it all back in then to the equation
Mhm.
to find the focal length.
Yeah. That's no problem. I figured it out.
Word.
All right. Next question.
Yeah.
So, identical ideal batteries are connected in a different arrangements to the same light bulb as shown in the figures. For which arrangement will the bulb shine the brightest?
So obviously it's not A.
Yeah.
I thought it was pretty obviously not B because that's positive to positive.
Yeah.
I think that would create a little issue.
Mm-hmm.
Yeah.
So it is circuit C.
Yeah.
I just knew that's what series is, and like in electronics, you can fry it if you run your battery in series without like any protection on it.
But also, like, all right, I looked something up about this and said if you have two if you have two light bulbs of the same that are identical,
Mm-hmm.
then the brighter one is the one that has the higher current. And
Right.
since C is just it's the exact same setup, just with double the voltage, then it would just be double the current as well.
Yeah, isn't it I is equal to V over R or something? I always forget these.
Yes, I equals V over R.
So if you doubled V, then you double I effectively. So that that would make sense because it's more particles passing through it, able to give off. Okay, yeah, that conceptually makes sense.
Okay. This one I did not get at all.
Yeah, so are we supposed to imagine, like, if we were doing a right hand test, then that direction would be where your fingers are, like where the electron's going?
I don't know.
So let me think about how I set this one up.
Yeah, that seems like it's right. Because if you did a right hand test and you thought to yourself, like, okay, the magnetic field is pushing the electron that way, so that would be where your thing is, like your thumb points into the screen. That could be wrong, though.
Which right hand rule is that?
For the magnetic fields.
Okay.
Or no, but the direction of the magnetic field. No. That would be the direction of the current that generated the magnetic field.
Mm-hmm.
Yeah, this question was a bit confusing. The direction of the magnetic field. Is magnetic field called B?
Yeah, magnetic field's B, current is I, and then force is just F.
Okay. That didn't really help me.
Yeah, because
Yeah.
I think what you're looking at is like, what's the magnetic field at like whatever location from some distance from a current, right?
I guess
The
so.
M0 one.
Yeah.
Yeah, I literally don't know how to.
As electron under the influence of magnetic force. Direction of the magnetic field.
Because if you place, I think, so you have to think about the current as well, because the electron's going to travel in the opposite direction as the current.
Oh.
So you have to, so like if you were to do the right hand rule, not thinking about the current, your thumb would go in the direction towards the top of the screen, and then when you curl your hands, it comes out. But if you flip your thumb and you curl your hands, it goes into the screen. Because the current's going in the opposite direction.
So, all right, electrons go perpendicular to the current.
They go
Is that what
opposite the current.
Opposite to the current.
They go opposite to the current because Benjamin Franklin wanted to make the current positive movement.
Mm-hmm.
So that means every single time you find a current, the electrons are going in the opposite direction. So I is like where your thumb direction goes. So if you think about it, if we thought about current, like say this was a positive particle, it would be going out of the screen. Because when you face your thumb in the direction of that, with your palm facing, with it like perpendicular to, I think, the force too, like the effective force on the electron, or in this case, positive particle, and you curled your hand, your fingers come outwards, but you have to flip it because it's negative and your fingers go inward.
Hmm. I still don't get this at all.
Yeah.
Yeah, that's tough.
Hmm.
Like,
All right. So we're using the right hand rule where you have like your palm open and flat, correct?
I'm using the ones where I twist my hand.
Oh, like you curve it?
Yeah. There's a way you can do it when you twist it too, I think, because that's how I did it. The wrong
That's-
way to get the right answer, but
I mean, that's how I did it and got the wrong answer. So, but I just,
I don't think you flip the direction of the current. I think that's the problem.
yeah. Right, so,
What you have to do is you have to assume, well, the electron's going to start moving in the direction of the current. So, like, it looks like the electron started going straight, right? Like it was going horizontally across the stream, and now it looks like it's starting to, and it almost looks like the effective current is bringing it upwards, right?
yeah. So,
Current is like, does that kind of make sense? So, but you have to flip the direction of the effective current, so it looks like it's going upwards, but it's actually going downwards.
oh, so the current is going
Down. So when you
down?
put your thumb in that direction and you curl with your right hand, it pushes your fingers outwards.
Okay. So, okay, so this is just an electron traveling to the left that interacts with a
It
current.
interacts with a current.
And since the current is going down, then the electron goes up and to the left?
No. So the electron, oh, yes. Because the current and the electron, they're going to have, it's like a vector addition kind of thing. I think that's happening. It's like slowly turning the direction of the electron. And so I think the main point about this is, well, you obviously know the electron was traveling horizontally, and then the current is pushing it upwards. But we have to think that because the current, the way it's defined by Benjamin Franklin, because he's a dumbass, is the direction of the positive charges, like the direction of the movement of the positive charges. So we have to flip that for the negative charges.
All right, I think I get this.
So you put your thumb in the direction of the current, the effective current, and the effective current, because it's a negative charge, won't be that upward direction like we're seeing. I think it's that downward direction. So when you curl your hand to get the direction of B, it comes out at you.
Okay.
I think that makes sense, yeah.
All right, I think I get them. Okay. Number 7. Oh, man.
Yeah, does anyone know how to do this one? Because I did not get this.
I just I was pretty much between A and, or rather, B and C on this one,
Mm-hmm.
and I was just like, yeah, I feel like on the on the first exam it looked like that, so I chose it.
Hmm.
I want to say the top one's n equals 3, the middle one was n equals 2, and then the bottom one was something else. Or no, the top might be n equals 1 actually.
Yeah, this is n equals 1. I'm pretty sure this is n equals 3.
Yeah, like if you could imagine, for every, like there are two states of the wave. There's like, you know, the positive and negative trough and like valley of the wave. I'm pretty sure it's just that it can exist in either conformation for both HOMO electrons. You know what I mean? So just double it.
All right, let's see.
Makes sense.
I basically just looked at the slides from from class a couple weeks ago when we did something like this, and it was pretty similar, but there was an extra arrow right here, and the correct answer was something that just had the two things. It was a lot like this one, except there was no space in the middle.
I think those are p orbitals.
Yeah.
Yeah. I feel bad because I should know this because I've been doing this stuff in chemistry, but I just forgot.
Yeah. I feel like I did it so long ago, and I haven't needed to think about it for so long.
You know,
It's just gone from my mind.
Yeah.
Chem 111 has been far gone out of my head. Probably shouldn't forget that.
Yeah.
Right.
I feel like that's a lot. Quite honestly, I feel like if I were to pick the most important year in chemistry, I think that is the most important.
Yeah. All right. All right. So it's C. We don't really know why. I mean, it kind of makes sense because, like, if
Okay,
you
it looks like looks like you can make three like halves of a wave out of it. You know, because you have up, and then you have the down, and then you have the up again. The looks like it's half of a wave. So, and then A, it would be n equals 1 because you can make one full wave going around it, I think.
Oh, that's true.
yeah.
So I think it's actually literally just looking at the shape of it. Because if you look at A, the shape of A, it just goes up and then around. B, it goes one half of it, then one half of it. And then C, it's like thirds.
Yeah. All right.
I would go as far to argue that how many electrons you have in it is how many like orbitals you're going to have on the top half, or electron density clouds you're going to have on the top half and bottom half.
Right.
Okay. All right. I don't know if that's right. All right. So number 8. This one took me a very long time.
Yeah.
A very, very long time.
Partially right.
But
Most proteins are negatively charged. It's negatively charged, so it'd go to the top half plate, obviously.
all right. So for this one, we have to find the acceleration of the protein. So to do that,
X equals ma.
yeah.
So
And since we're given the mass, we just need to find the force. And force for, what are these parallel plates? Force for this is QE, which is charge times energy. Then E is Q over A epsilon, which is all on the equation sheet. And then, so we have Q, we have E, we have Q, we have epsilon. And A is, it's part of a, what's it called? Capacitance equation. So there are two different capacitance equations. There's C equals Q over delta V. And we know both Q and delta V. And the other one is A over, epsilon times A over D. And we know epsilon and D. So what I first did is I set Q over delta V equal to epsilon times A over D to find A. Plugged that into the equation E equals Q over A epsilon to find E. Plug that into force equals Q times E to find force. And then after that, acceleration is just force over mass. And it's a bit confusing, but I got about 4,850 meters per second squared. But
A lot of work that I didn't do, but I also got one of the answers, so I'm kind of pissed about that.
also, we know it's accelerating towards the top plate because this
Yeah.
top plate is positive and the protein is negatively charged. All right. So how did you do it?
I'm trying to look at my work right now. Okay, so I did. I tried to find. Huh. Oh, I did volts times coulombs. So I did the battery voltage times the protein charge, I think. I don't know what prompted me to do that because I don't write down any of my work and it's probably really bad of me to do. And then I divided by the protein mass. And then I got the answer that I got.
Okay. So you did.
I think it was just a very nice coincidence that it ended up being one of the answers on the thing.
So you did voltage times the charge of the protein
Yeah.
divided by the mass. Okay, let's see.
Divided by the protein mass, yeah.
Divided by. I just did that and it did not give me the right answer.
Yeah, I didn't get the right answer, but I got one of the answers. So I was like, convenient.
Oh yeah. Okay. Yeah, I actually I looked at this video, which helped me a lot.
Oh,
Mhm.
okay.
Um,
I was about to ask how you got E. Because
Well-
I definitely know you need the capacitance thing, right? Because it's a capacitor.
yeah,
The K epsilon A over D.
yeah.
I don't know, that would be a dielectric constant. But does it have the area?
Oh, that is what we're trying to solve for. That is what A is. Well, okay.
Oh.
It's not what we're trying to solve for in the end of the equation, but if we set it up the way I did, that is the thing that you have to solve for.
Oh. Okay.
Did you happen to write down your work on a piece of paper?
I can do that. I can rewrite it neatly.
At some point, if you want to pop that into the Discord chat,
Yeah.
or like a private chat or whatever, it doesn't matter.
I'll put it into the Discord. Okay. I'll do that later. So go on to the next one. All right. The refractive index of material A is greater than the refractive index of material B. A ray of light is incident on the interface between these two materials in several ways, as the drawings illustrate. The dashed lines denote the normals to the interfaces. Which one of the drawings shows a situation that is not possible? To be honest, the way I did this is I went to the textbook and where is it? There was just hold on. If you go to the textbook, read book, contents. Producing images, I think it's here.
I have it in my notes somewhere. If it...
Man.
Hey, what are you guys going over?
we're
Going,
just doing the practice exam.
yeah,
Oh, okay, cool.
we're on
Yeah,
question.
we can kind of go into the problems for it, and now we're on number 9.
Yeah,
Been recording it so far, and quite frankly, our logic is shoddy, but it's getting us there.
yeah.
Okay, cool. I took the practice exam, so if you guys have any questions, I might be able to help out.
Yeah, I
Yeah,
think
I think we all took it.
Oh, okay, cool.
The answers.
we
I think what we're doing is we're just like especially going through it, see who got what right, and trying to look at their logic and kind of understand what they did.
Mm-hmm.
do you know how to do this one? Because I got the right answer, but I kind of guessed. I
It's
didn't really solve it out.
for that one, it's just that the electrons in n equals 2 states, so that means there's going to be 2 half wavelengths. So you just want one that's going to look like basically has, how do I describe it? It's like if you were to trace the curve
Okay,
of
so
the
that's kind of my
electron fields.
Yeah, yeah.
I got it wrong, but
Okay.
thinking about it now, that was what I was saying earlier.
All right. No, we went over that one. This one, I don't remember what
Well,
part
if
it's in.
so when light enters a new medium and its speed, or rather, if and it speeds up, the ray bends away from the normal line, and if the speed decreases, it bends towards the normal line. So, yeah, you would just
Okay.
have to see like what the refractory indexes for both of them were, and since that bent toward the normal line, I'm sure it was supposed to be like speeding up when it entered the A material.
I just used this simulation to figure out most of the stuff. It's under the law of refraction in the textbook.
Cool.
But yeah, I just basically did these out. Okay. Number 10. There are two metal spheres suspended by metal threads as shown below. The right one is negatively charged, the left one is neutral. They're identical spheres. So both spheres feel an equal attractive force. They hit each other and then they experience an equal repulsive force. The way I logicked this out is that, I knew that a neutrally charged object is attracted to both positive and negative things. So these things would both attract. And then I imagined that the right ball would give some of its negative charge to the left one.
Yeah.
They would just repel each
Yep.
other.
Yep.
All right.
That's also how I thought of it.
Okay. I got like partial credit for this. Apparently.
Hmm.
I don't get this.
I have the equation out. No, I didn't do it. I just have it written down from the SI review session.
Mhm.
Okay.
But so he said to use the equation energy final minus energy initial will equal Q plus W. And then you can solve for Q. And then once you have Q, oh, well, that will give you the energy. And then you can use energy equals hc over lambda to get the wavelength.
I think I did something like that, and I got a royally incorrect answer. I'm very happy with myself about that. What I kind of did is I thought of it as like the kinetic energy of the photon has to equal the kinetic energy of electron plus the work it put in.
Yeah.
So I think my issue I think I messed up with the conversion of electron volts to joules because I just hate electron volts.
I know, I always get confused with converting them. I always forget how.
I think I just messed up with my conversion, to be honest.
So I think what this one should be, the equation should look like 9 EV minus 0 EV equals Q minus 8.3 EV. And solve that to find Q.
Yeah.
And that will be your E for your E equals HC over lambda to get your wavelength.
So wouldn't that
makes sense?
be 9 plus 8.3?
Yeah, like if you would end up doing E final plus W
Yeah.
will equal your Q. Yeah, it's actually that's a lot simpler to look at it that way.
I was just thinking of it in terms of like kinetic energies because like energy is neither created or destroyed. So whatever the photon had originally, assuming the photon loses all of its kinetic energy once it hits the metal plate, what it does is it has to dissipate all of its all of its energy to the electron and the work to move it.
Mm-hmm.
So I was just thinking like the total energy of the photon has to be what's left of the final kinetic energy of the electron plus whatever work it did to get it up there and out of that plate.
Got you. Yeah, that makes sense. And then you just have to make sure once you get your wavelength, make sure you convert it to nanometers.
Yeah.
Yeah.
All right.
So yeah.
Sorry, did you say you had to convert it to joules or something?
I don't think you have to. Actually, wait, no, I think you have to. But
Yeah.
I messed up with my conversion.
That might be why I got the partial credit because I didn't convert to joules at all. How do you convert to joules, by the way?
I
It's
just
just on the
It's times 1.0256 times 10 to the negative 18th.
Send the negative.
I'll just type that in here for you.
Okay. So you multiply that by the EV, correct?
Mm-hmm.
Yeah.
-18.
Yeah, that's probably why you got partial credit, because he probably has one of the options as being if you didn't convert. So he was probably like giving you like some credit, for that.
Yeah.
I probably right. Thanks, Brock.
I'm so
Um,
glad you pushed back the due date for the lab.
oh yeah,
Yeah.
holy shit.
I'm like close to finishing, but I'm so stuck on the last part of it, like 20 through 22 or whatever it is. Or
I think
20
I'm like around there as
If
well.
you need any help, text me. I finished it.
Okay, yeah, I probably will, because I'm just really confused how to figure out the RO. Like, I don't understand at all.
Wait. Do you have Snapchat? I'll put my Snapchat in the thing.
Okay, cool.
It's not very complicated.
All right. I still don't get this one because
Which one?
whichever one we're on, 11.
Oh sorry.
Oh no, go ahead.
Oh, I was wondering why the final kinetic energy was 0.
Oh, the final should actually.
Oh, is it for the photon or no, the electron?
The
The final kinetic
Oh,
energy
never mind, never
of
mind.
the photon would have to be 0, assuming
Yeah.
it's absorbed into the metal plate, because
Yeah,
it
yeah.
would be moving.
I kind of answered my own question.
You're fine.
Yeah, no, this makes sense.
So even when I do convert to joules, I still get the same answer.
Oh, really?
Yeah.
That's strange.
Let me try this.
Are you using E equals hc over lambda? For the
What am I using? Yeah. E. So the equation ends up being lambda equals hc over e.
Yeah. Interesting. I actually didn't get this one right, so I only figured out how to do it in the review session. So I'm not sure what my answer was, but
And it's really weird because I got partial credit for this.
I got partial credit too.
All right.
That's so weird.
Yeah. All right. Do y'all want to move on?
Yeah.
Okay. So,
Hey Wyatt.
Hello.
What's up?
the
Oh,
okay. So for these questions, which light wave represents higher energy protons? Photons is wave 2, because the shorter the wavelength, the higher energy. Which light wave represents more photons? Wave 1. I think that goes with the amplitude.
Yeah.
Yeah.
This
Oh,
is
for the second part, yeah, it's that was confusing me too with the both wave 1 and wave 2 versus the waves are the same. I didn't
Yeah.
know like which one to put.
The waves are the same because they're both light. They're both traveling at the speed of light.
yeah. The wording is weird.
Yeah.
If you think about it, this wording is technically more correct than the other one. But hey,
Yeah, that
I'm
kind
not
of
the
tripped
one
me up
grading
as well.
yeah. So
Yeah, when you think of photons, just remember that photons are massless. So in that concept, you're still focusing on the speed of light regardless.
Mhm. All right, so for which light wave might you see a photon at x equals 1,000 nanometers? It is this one, wave 1, because, what is it? The square of the amplitude is the probability?
Yep.
Is that gonna right there?
Yeah.
Okay.
You can also just see because like on wave 2, it's at 0, which would mean there's like probably no photons there.
Yeah.
Right.
Yeah.
Which light wave will exert the larger maximum force on an electron as it passes by? It's wave 1. I kind of guessed on this one, so does anyone know why?
Okay. Which one exerts more force? I can't remember why.
Yeah, I said wave 2 just because I thought the shorter wavelength, but
Mhm.
yeah, I don't know.
Well, you got it right, so
Yeah.
I think because there's more photons
That's
in
true.
wave 1 and it's stronger, it's going to be able to exert a larger maximum force on an electron just because it has more charge.
Okay.
Can one electron absorb like multiple photons?
Yeah, that's how it gets up to like multiple like emits more light.
Right.
Like because when it absorbs an electron, it goes when an atom absorbs a photon, it moves down it moves up in an energy level. So I guess it's depending on how many
Okay.
if we're thinking about like Bohr's model, how many rings it has, I guess.
All right.
Or
Then
subshells.
it's that if both light waves are in the visible wavelength, which is more towards the blue end of the spectrum, wave 2, it's just the shorter the wavelength, it goes more towards the blue and the purple colors. For this one,
Yeah.
you can literally just look up color wavelengths, and there's a million things online.
You can also look at a rainbow because like red is always on the outside because it has the longest wavelength.
oh, I didn't think of that.
I didn't think of that. Yeah.
That's why rainbows are the color order they are. It's kind of weird.
Ooh.
All right. If a single photon of each were emitted, one from an electron undergoing transition A, which is the second energy layer first, and one from transition B, which is third to first, which would be emitted from transition A. It's wave 1 because the transition B requires more energy, it's it's giving off more energy than transition A, and we have already figured out that wave 2 has more energy than wave 1, so it would just be wave 1
Yep.
because it has less energy.
Right.
Okay. Now 13. This was incredibly weird because there's like no real instructions other than this stuff.
I honestly had I was like so confused this entire thing, and I had no idea how to do it.
Yeah, me neither.
Try to attempt it, because I mean, like, I tried to attempt it, and I don't think my answer is right, but
I
Alright.
have a solution out for it. Let's see. Did anyone else figure it out?
I tried. I don't know if it's right, but
Okay, let's see.
that's what I got.
What is the charge on the capacitor?
oh my god, I got that too.
So, how did I do this?
Wow.
I forgot how I did
Wow.
this, to be honest.
So you
But-
use the equation. You have to use the equation. Volts is equal to I times R plus, I think it's Q over C.
Yeah, so
And because it's in parallel, you can forget about the resistor in this moment in time.
Mhm.
And you just have to think 24 is equal to blank over 12. Because you know, Q over C, C is your capacitance, and farads are your capacitance,
Mhm.
and volts are your volts.
Yes,
So you do
that's how I did it.
24 is equal to what energy over the capacitance of the capacitor. You get 288.
And then.
But I
or-
said over time the charge will dissipate, the charge is gonna have to dissipate a little bit because the resistor over time like slowly dissipates the charge on a capacitor.
Oh, okay.
I just thought that once you flip the switch, the charge will accumulate in the capacitors, and at the time equals infinity, it would be 288.
Okay.
I'm not sure. It says from David's SI session, it just says about 288 coulombs.
All right. I like
You didn't-
the using the capacitance equation. That's just
Yeah.
simple.
Yeah.
So. And then for part B, since the battery is just taken out of the equation, that doesn't matter. So the 228 volts from the previous question plus the resistor is 0, and we know the resistance of the resistor because it's 3. You just solve it out to 96. What's this unit? Is it ampere? Amps?
Yeah, amperes are the measure
Ampere.
of current.
Okay. I knew the letter, just not not what you call it. Okay.
Okay, so actually I think that was the one I think we were the most cohesive on
Yeah.
when it came to answers.
So let me go back through this one more time. This I understand. Still don't get this one 100%, but I got partial credit.
One more time.
Sorry, say that again?
So wait, do you want to talk about it like conceptually one more time now that we're all here?
Yeah, just like because I understand that you have to do like the change in energy. So you start with some number. You start with some EV,
Yeah.
and then you add 8.3
So-
EV, and you get 9. So the starting EV for this one is 0.7, and I get all that. I get the equation where you do lambda equals hc over e. I'm getting something that's apparently wrong.
Let me try and solve it out real quick with your numbers and see. I'll tell you what I get.
All right.
Yeah, I got your answer when I did it out.
1771.4.
I just got 71.7 nanometers.
Oh, how did you do that?
I just
Um,
thought that too. Wait, let me get back to the actual answer. Wait, what number is it?
71.7 nanometers.
Yeah.
So
my-
like what came out of my calculator was 7.17 times 10 to the minus eighth.
Yeah, I got that.
Okay.
So what you have to do is you have to think about, when you think about the energy of the system as a whole, you have to know that the total energy of the system is the energy of the photon coming in. So you add the work and the final kinetic energy of the electron together to get the total energy that the photon had coming into the system.
Oh, you add them together?
Yeah.
Yeah.
Oh! Okay.
Were you minusing?
Yeah. Yeah.
You end up getting, because like if you think about it, the photon is bringing all of the energy into the system, right? So whatever energy that photon is putting into the system is the energy output that the electron is going to have plus the work that the photon had to do. Does that make sense?
Sorry, could you say that again? I was putting something in my calculator.
Like, because the photon is realistically the only force that's bringing like any kinetic energy or energy realistically into the system,
Mm-hmm.
because that metal plate's really not doing anything. The entire energy of the system of that photon is going to be put into a moving the electron and giving the electron its kinetic energy.
Mm-hmm.
So you know whatever energy the photon had is going to be the additive sum of the final energies of the system. So you know it's going to be what energy it put into doing the work and what energy that the electron has. So when you add those together, you get the energy of what that photon had.
Oh, so is the work taking away energy?
No, the work is the energy, additional energy that that photon had to do to move the electron. Like, think about the work. I thought about the work in terms of it's the energy that the photon had to use to knock the electron out of its spot.
Hmm.
By the way, guys, sorry about this. I apparently had the wrong conversion factor for EV to joules. It was just that was the number of joules in the equation, but it's actually I'll just type it in the chat for you, but it's a different number.
Yeah,
I
okay.
just literally look up joules to EV on
Yeah.
Google every time, and I type it in.
Yeah.
Yeah, you can
I
just look it
never
up
worry
too.
about it.
The equation sheets that he gives us, they're so helpful. It's got basically all the stuff on there.
Yeah.
Okay.
But so once you get, like, once you kind of understand the concept, like the photon is putting all of the energy into the system, and because energy can't be created nor destroyed, whatever the final product of that energy is, assuming that thermal energy is kind of like not really happening right now, even though you know it has to be happening, so there has to be energy dissipation that you can't measure. But assuming that's like not really going on, you can add the work and the kinetic energy together, because you know that the final energy, or like the initial energy, is the sum of the final energy plus the work it took to get it there.
Hmm.
When you do that, you get the energy of the photon that it came in initially with, and then you can plug that into the equation. E is equal to hc over lambda. And now this is where you convert, this is where you convert the electron volts to the joules.
Okay.
I think you need to convert the electron volts to joules. That's how I got the right answer when I did it.
You don't need to. I kept them as electron volts, and I mean after I got the right number of electron volts, it still works. I got
Oh,
71.
really?
Yeah.
Okay, cool.
Wait, really? Do you use a different H? Because the H I used was in
Yeah.
joules. per
Yeah.
Kelvin.
There's two different H's.
Oh,
There's
okay.
one for joules, one for electron volts.
Oh yeah, then it doesn't matter.
Well, I used the one for joules, and I think that's what screwed me over.
That may have been it.
But once you plug that into that equation, just flip-flop the E and the lambda, and then you get yourself lambda is equal to hc over E.
Mhm.
And that'll give you your answer.
Yeah.
All right, I gotta head out, fellas. Sophia, do you mind if I add you if I have a question about the lab? Because I've been pretty lost.
Absolutely not. Please add me.
Huh?
You can add me.
Okay. Cool. All right. Well, it's been good studying, fellas. I'll talk to you later.
All right.
Sounds
Yeah.
good. Thanksgiving.
Yeah. Have a good Thanksgiving. All right. Okay.
I'm probably gonna try to finish this lab. Honestly, I'm just really stuck on it. Have you guys finished it yet? By Sophia, you have.
I have.
You have too.
Yeah. All right. So if we're done with this, I'm gonna stop the recording.
All right. Cool.
Okay.